Just a recap, we looked at Boyle's law, and it states that for a fixed mass of gas, volume is inversely proportional to pressure at constant temperature. We went through deriving the equation that we are going to use in the calculation when working with Boyle's law. The graphs for Boyle's law, we have P versus V, or vice versa. So the P is on the y-axis and the V is on the x-axis, but you could have the V on the y-axis and the P on the x-axis. Similarly, P and 1 over V, where P is on the y-axis, 1 over V is on the x-axis, you could have V on the y-axis and 1 over P on the x-axis. And here we have PV on the y-axis and V on the x-axis, PV and P. All 4 graphs here represents Boyle's law. All right, so let's look at a particular calculation using Boyle's law. A balloon contains 7.2 liters of helium. The pressure is reduced to 2 atmospheres, and the balloon expands to occupy a volume of 25.1 liters. What was the initial pressure exerted on the balloon? So the first thing you want to do is to go through and write down the information that you know and what you want to find. In this case, we know V1, which is the initial volume. We don't know the initial pressure, so this is what we are looking for to calculate. And we know the final pressure and the final volume. Using Boyle's law equation, P1V1 equal P2V2, we are now going to sub to make P1 the subject of the formula and put in the information. Right now, we can work with all the units we have here, since we are going to just plug in the information and get the pressure that we want. So our pressure in this case for P2 is 2 atmospheres. For the volume, V2 is 25.1 liters and V1 is 7.2. Plug in those values and cancel out the units. You end up with 6.97 atmosphere. And so the question asks, what was the initial pressure exerted on the balloon? So the initial pressure exerted on the balloon was 6.97 atmosphere. Remember, it's easy to convert from atmosphere to Pascal, because 1 atmosphere is equal to 1.01 times 10 to the 5th Pascal. Let's look at another question. In this case, 352 milliliters of chlorine under a pressure of 680 millimeter mercury are placed into a container. Please remember that millimeter mercury is a unit of pressure. And so this pressure of 680 millimeter mercury are placed into a container under pressure of 1210 millimeter mercury. The temperature remains constant at 296 Kelvin. Remember that Boyle's law deals with changing the pressure and the volume and keeping the temperature constant. So what is the volume of the container? Putting down the information we have volume 1, which is 352 milliliters. We have pressure, which is the initial pressure, 680 millimeters of mercury. We don't know the final volume, and we have the final pressure of 1,210 millimeter mercury. Using the equation and solving for V2, you make V2 the subject of the formula, plug in the information, and here we have our value of 197.82 milliliter. So the volume of the container is 197.82 milliliters. If you want to convert milliliters to liter, you will recall that 1,000 milliliter is equal to 1 liter. So you could do that conversion easily if required. Let's now move on to looking at Charles' law. And again, a quick recap. Charles' law states that for a fixed mass of gas, volume is directly proportional to temperature at constant pressure. So in this case, our pressure is constant. So we look for this in the equation. Going through deriving Charles' law, the equation, volume is directly proportional to temperature. So remember again, we remove the symbol here, put the equal sign and a constant, and we end up with V1 over T1 equal V2 over T2. And this is the apparatus using heat from a flame, water in a beaker, and we have a capillary tube attached to a ruler that will tell us when the volume is increased or decreased based on the mercury plug moving up and down. You will never find in this case where the mercury plug is all the way down to 0 because you'll always have some volume of gas present in this container. And the thermometer will tell you the temperature going up or down. We will recall again the graph for Charles' law, that this part is representing that you will always have a volume. So the graph will not start at 0. This straight line is suggesting that volume and temperature, they are directly proportional. We spoke about absolute 0, and this is the lowest temperature possible. All right? This will be 0 degrees Celsius. And right here, you'll have negative 273 degrees Celsius, which is 0 Kelvin. And that is our absolute 0. In looking at the calculations involving Charles' law, if you read the question, earlier we found that volume of oxygen can be obtained from a particular tank at 1 atmosphere and a temperature of 21 degrees Celsius. You have the volume of the container, which is 785 liter. What would be the volume of oxygen if the temperature had been 28 degrees Celsius? So you see, in this case, we want to find the volume if the temperature had been 28 degrees Celsius. So we have here the information. Don't forget that we have to convert our temperatures to Kelvin by adding 273. So the initial temperature, which was 21 degrees Celsius, is now equal to 294 Kelvin. The final temperature, which was 28 plus 273, would now give us 301 Kelvin. You'll notice that if you look at the question, you'll see that the pressure is constant at 1 atmosphere. And so once the pressure is constant, we know that we must use Charles' law equation. So note that temperature varies and pressure remains constant. So V must change. And these are the conditions needed to apply Charles' law. So we're using V1 over T1 equal V2 over T2, and we make V2 the subject of the formula. So V2 is equal to V1 T2 over T1. Plug in the information given and calculate the value of V2. And our value would be 803.69 liters. And so this would be the volume of oxygen if the temperature had been 28 degrees Celsius. In looking at another question involving Charles' law, a gas occupies a volume of 200 cm cube at 0 degrees Celsius and 760 millimeter of mercury. What volume will it occupy at 100 degrees Celsius and 760 millimeter mercury? Again, the first thing we need to do is to put down the information that we have. And remember that we must convert degrees Celsius to Kelvin by adding 273. So our initial temperature of 0 is equal to 273 Kelvin. and the final temperature of 100 degrees Celsius is equal to 373 Kelvin. The initial volume is 200 cm cube, and we want to find the final volume. So using the equation V1 over T1 equal V2 over T2, we are going to make V2 the subject of the formula and plug in the information and cancel the units that we don't want, leaving V2 to be equal to 273.26 centimeters cube. Now we're focusing on the ideal gas equation. We must recall how it was derived from both Charles' law and Boyle's law. If you do the revision, you'll see that once we combine both Charles' law and Boyle's law, we will end up with the ideal gas equation, which is PV equal nRT. We then showed you how you could use that very same equation to work out molar mass or work out density. So we just simply change N to M over molar mass. And then once we have mass, we combine the mass with the volume to provide density. And now we have molar mass equal density times RT over P. So this equation can be used if we're given density in the problem and we want to find the molar mass or temperature or the pressure. These are some units that you must remember that will be helpful in your conversion. So pressure is in Pascal or Newton per meter square. Volume can be in meter cube, liter, dm cube, milliliter, or centimeters cube. The unit that will be used will be based on the R, the molar gas constant that is given. So right now we're using meters cube. Moles is in, of course, MOL, mole. And in this case, we're using the R to be 8.31 joules per Kelvin per mole or joules per mole per Kelvin. And the temperature is always in Kelvin. So if it's given in centimeters cube, you must convert to Kelvin. These are some things that you'll be used. These are some things that you'll be using to help with converting from one unit to the other when we have a particular R working with, whether it is in joules per mole per Kelvin or liter atmosphere per mole per Kelvin. Let's move on to some questions dealing with the ideal gas equation. In this case, we are going to determine the volume occupied by 2.34 grams of carbon dioxide at standard temperature and pressure. The first thing you must remember that when I say standard temperature and pressure, the temperature is 0 degrees Celsius, which is really 273 Kelvin, and the pressure is always 1 atmosphere, or 1.01 times 10 to the 5th Pascal. Or you could say, you could work that in kilopascal if you wish, but when doing the calculation, you should convert your kilopascals to pascals. And remember that Pascal is the same thing as Newton per meter square. So given the information that we have, we want to find the volume. And we start with the equation PV equal nRT. We make V the subject of the formula. So now we have nRT over P. In the question, we're given the mass in grams. And so from that, we can find moles. And moles is equal to mass over molar mass. The molar mass of carbon dioxide is 44 grams per mole. Once we know the mole, and remember that in working with standard temperature and pressure, we know the temperature already, and we also know the pressure. And the R that we're going to be using is 8.31 joules per mole per Kelvin. So we just plug the information in the formula. Now notice that we have moles here, and here we have joules per mole per Kelvin. So the mole would cancel the mole here, and the Kelvin would cancel the per Kelvin here. So the unit at the top here would be joules. Then we have down here pressure, which is Newton per meter squared. Now, you would recall that Newton is kilogram meter per second squared, but I have per meter squared here. So if I should write out the unit for this part, because remember now, we removed moles and Kelvin, so I have joules over Newton per meter squared. So let's see how that would work out. So if I have joules on top and below, I have Newton per meter squared. Remember that joules, let's show you, joules is kilogram meter squared per second squared here. And Newton is kilogram meter per second squared. So I'm going to use this section right here to work out the unit. So if I write kilogram meter squared per second squared over kilogram meter per second squared, and then I have here per meter squared, so I'm going to have divided by meter squared. So let's write this one in a similar fashion. So I'm going to have kilogram meter squared per second squared over kilogram meter per second squared over meter squared. So I'm going to write this now by saying kilogram meter squared per second squared divided by kilogram meter per second squared per meter squared. So this will now give me kilogram meter squared per second squared divided by kilogram meter per second squared per meter squared. So we're now going to multiply this by this, and therefore this part will be inverted. So I have now kilogram meter squared per second squared multiplied by second squared meter squared over kilogram meter. So you'll see now second squared will cancel second squared and meter would cancel meter there. So what I have left would be kilogram meter squared. But if you notice here, I still have a kilogram here. So kilogram would cancel kilogram. So all I'm left with is meter squared times meter, which is meter cube. So this is the unit. Now, if you work this out using atmosphere as your pressure, it should be simpler to calculate. But I have to show you both methods just in case that you get the units like joules and Pascal to work with. You know how to do the conversion. So let's go back to the question. So if you notice here, joules over Newton per meter squared is what we just looked at to convert this volume to give us meter cube as our answer. So the volume occupied by 2.34 grams of carbon dioxide at STP is 1.19 times 10 to the minus 3 meter cube. Let's look at another question. Now in this question, I'm going to show you how we work it out using our R as 8.31 joules per mole per Kelvin, or R equals 0.0821 liter atmosphere per mole per Kelvin. Let's look at the first one. A sample of argon gas at STP occupies 56.2 liters. Determine the number of moles of argon and the mass in the sample. Again, looking at the ideal gas equation, PV equal nRT. We need to make N the subject of the formula. Therefore, N equal PV over RT. Once I find moles, because the question wants to determine the mass. So once I know the mole, I could now use mole equal mass over molar mass to find the mass. Okay, so I'm using the calculated mole and the formula mole equal mass over molar mass to find the mass. I'm using my pressure. The pressure given is in atmosphere because it is atmospheric pressure. And so I convert 1 atmosphere. And see, it says standard temperature and pressure. So the P is 1 atmosphere, but I want to work it in Pascal, which is Newton per meter squared. So I convert 1 atmosphere to Pascal. My volume, which is in liter, I will convert to meter cube. And I use the conversion factor of 1 meter cube equal 1000 dm cube. And so my answer for volume is in meter cube. Once I have my pressure in Pascal and my volume in meter cube, I must use 8.31 joules per mole per Kelvin. Again, my temperature must be in Kelvin. So I add 273 to 0 because standard temperature is 0 degrees Celsius. I now plug the information into N equal PV over RT, put in the pressure, put in the volume, put in my R and my temperature, and I do the conversion. So here, if you work it out the way I just showed you earlier, you would see that I'd end up with joules at the top and joules per mole at the bottom. And of course, joules divided by joules per mole will leave my unit to be mole. So my answer is 2.5 moles. I now know the number of moles. I can now find the mass because I know the molar mass of the sample. And the sample is argon. So the molar mass of argon is 40 gram per mole. And so mass is equal to moles times molar mass, which is equal to 100 grams. This is using my R as 8.31 joules per mole per Kelvin. Let's see what happens when I change the value of the R. So now, same question, but my R is now 0.0821 liter atmosphere per mole per Kelvin. Notice that if I'm using this R, my pressure must be in atmosphere and my volume must be in liter. My temperature, I must convert to Kelvin as usual. Again, it's much simpler with the units, so I just plug in the information here, and I have 1 atmosphere times 56.2 liters over 0.0821 liter atmosphere per mole per Kelvin, and a temperature of 273. And when you look at removing the various units, you'll end up with your answer in moles. Again, we just simply now say mole is equal to mass over molar mass. Therefore, mass is equal to moles times molar mass, which gives you the same value of 100 grams. Now, moving on to question 3, we have this question saying, at what temperature will 0.645 moles of neon gas occupy 12.30 liters at 1.95 atmosphere? So here, I did both methods. You'll notice that the answers will vary slightly, but it's pretty much correct. In this case, I use atmosphere and 0.821 liter atmosphere per mole per Kelvin as my R. So the question requires the temperature. So using PV equal nRT, I would just make T the subject of the formula. Therefore, T equal PV over nR. You notice that I have my pressure, I have my volume, my number of moles, and my R. And I just plug in those information, do the conversion with the units and the cancellation of the units. And I get my answer to be 44.17 Kelvin. If I'm using R to be 8.31 joules per mole per Kelvin, then my pressure cannot be in atmosphere. I must convert it to Pascal. I must convert my volume in liter to meters cube. And of course, the mole was given in the question, and I'm using R as 8.31 joules per mole per Kelvin. I just simply plug the information in the equation, and my answer given here for temperature is 445 Kelvin. So you can work it in atmosphere or Pascal if you so desire, or depends on the one that the question requires. The final question we look at today is, Question 4. A 30.6 gram sample of gas occupies 22.414 liters at STP. What is the molecular weight of this gas? So you want to find the molar mass. But you could simply see that this gas at standard temperature and pressure, STP, would give us 22.4 dmq per mole already. So if we get this gas, this of course is saying that this mass is for 1 mole of the gas. So we could simply use that to come up with our answer, that our answer for the molar mass is really 30.6 grams per mole, just by looking at this information that we know here about STP. But if you're having issues with that, you could go ahead and use the formula. PV equal nRT, convert moles to mass over molar mass, and make molar mass the subject of the formula. Plug in the standard temperature and pressure, and your answer will be calculated to 30.6 gram per mole. Thank you.